As we move on, we're going to talk about a new term, and this term is what we call the odds. The odds describe the likelihood of an event as a ratio comparing the number of favorable to unfavorable. So the odds in favor are how many there are that we want. Okay, this top fraction is what we're looking for. And the bottom fraction is its complement, what we're not looking for. Okay? And then the odds against is just the reverse of the original. You do unfavorable to favorable. Now, one more thing, let's make sure that we talk about something called experimental probability. Experimental probability is based on data collected from repeated trials or repeated experiments. Makes sense, right? So experimental probability, we still write it with P of an event. You put whatever the event is in parentheses. You say how many times that event occurred and how many of times the experiment was done. Let's move on and apply odds and experimental probability. First, let's work with odds. What are the odds in favor of spinning, of the spinner, there's a fire alarm again, of the spinner landing on a number greater than or equal to 6? So what we are going to do is we're going to say, first of all, I see there are 8 sections. Now what we want to take a look at is how many of these sections are greater than or equal to 6. Well, we can say that that would be 6, 7, and 8. So there are 3 that are greater than or equal to 6. Next, how many are not greater than or equal to 6? Well, that would be 1, 2, 3, 4, and 5. So there would be 5, or the complement of the total, or the complement of how many there are 5 that are not greater than or equal to 6. So when we do odds, this one wants odds in favor. We put how many there are, so there are 3 that are greater than or equal to 6, against how many are not out of 5. Now, I just want to make a little note down here that odds are not the same as probability. Okay? Odds are not the same thing as probability, because in this example, the probability of getting something greater than or equal to 6 would have been a 3 out of 8. So it's very different. Now what you can notice is that odds in favor, if you add them, it will always equal the total. Maybe we should make a little note here, just to kind of help ourselves double check. If you add the odds, you will always get the total. So if you add the top and the bottom, you're always going to end up with the total possible anyway. Alright, let's take a look at the next one. It's the got it. It says, what are the odds against getting something less than a 3? Odds against getting something less than 3. So first of all, let's think of the ones that are less than 3. How many are there that are less than 3? Just 1 and 2, right? So there are 2 that are less than 3. How many, therefore, are not less than 3? I'm sorry, I just had a knock on the door. So how many are not less than 3? Well, that would be 3, 4, 5, 6, 7, and 8. So let's count those up. 1, 2, 3, 4, 5, 6. So there are 6 that are not less than 3. So since this time we're doing the odds against doing a number that's less than 3, we put the against on the top and we put the in favor on the bottom. So this time you put the against on the top, the in favor on the bottom. When we reduce that, we get a 3-to-1 ratio. And if you want to write it with a colon, you can. So you always want to make sure that you reduce when possible. Moving on. Experimental probability. Now remember, experimental probability simply means that, well, you had an experiment. Quality control. After receiving complaints, a skateboard manufacturer inspects 1,000 skateboards at random. The manufacturer finds no defects in 992 of them. What's the probability that a skateboard selected at random has no defects? Write the probability as a percent. So we're going to do the experimental, because he's doing an experiment, probability of no defect. I am so sorry about that fire alarm. And, well, how many did not have a defect? 992 over how many total? 1,000. Let's go ahead and reduce, we don't even have to reduce that because they asked us to find it as a percent. Now, make sure you note that you would absolutely have to reduce that if it asks for you as a probability itself. So we end up getting 0.992. So as a percent, that's 99.2%. And I guess I can make mine a little neater. 99.2% of them have no defect at all. And that's based on his experiment. Next, you have one more. You got another skateboard company. And this time they're going to select 2,500 and they find that 2,450 of them have no defect. So this time, what's the experimental probability of no defect? Same thing above. You're going to put 2,450 over 2,500. You're going to get a decimal. 2450 divide by 250. You get 9.98. And as a percent, this time, 98% of them had no defect at all. Now what we're going to do is we'll do this one more time, but we're actually going to use it. You ask 500 randomly selected households in your town if they have a dog. Of 500, 197 said that they have a dog. Now, what if you wanted to relate this to something bigger? Pretend that your town, so you have a little bit, you're using a little sample of 500, you want to relate that to your whole town that has 24,800 households. How many of those will probably have a dog? So what we're going to do is we're going to do the experimental probability of having a dog, and that was 197 out of 500. We may as well convert this to a percent. And we're going to say that, look how nice that number is. We're going to say that that percent is 39.4% of them, or as a decimal, 0.394. So what we're going to do is we're going to apply this to a bigger sense, and that's 24,800. So of those 24,800, if we simply multiply that, I'll use a big dot instead. If we multiply that by the percent or the decimal that we got, 0.394, so times 2,4,800, we get that approximately that many households, and we'll round up because you can't have 0.2 of a household. We'll say 9,772 households have a dog. And that's it. If we asked, by the way, how many don't have a dog, you would just, subtract that from 24,800. Now, is there another way of doing this? Absolutely. Let me just show you. Maybe you would prefer this. You could say, well, if it's 197 out of 500, and this is using a proportion, if it's 197 out of 400, or 500, how many would it be out of if you had 24,800? So you could cross multiply 197 times 24,800. So we get 0.488560 equals 500x. Just cross multiply, and now we divide by 500. You would see we get the exact same answer. We would get 977, round up to 0.2 households. It's approximate for x. So either way is completely acceptable. I don't care. This one will always be the most accurate because over here you might have to round at the beginning. So it's your choice as to which one you want to use. Let's try experimental probability one more time. And this time we have another manufacturer. He has 700 light bulbs, 692 of them work, but there are 35,400 light bulbs in all. How many are we going to expect? Now, that likely is very important. How many are likely to work? So we can say that the probability of it working is 692 out of 700. Now you can change that to a decimal, or you can use a proportion. I'll do both ways, so whichever way you choose. If you change it to a decimal, 692 divided by 700 is, look how we're going to have to round here, 0.98857. I would use a lot of decimals. And then you would say, so you got 35,400 times that decimal that we just got, 98857. Then you'd have to type that into your calculator, so times 35400. Notice I just hit the times button, so I actually did not round. And I get a total of saying how many should work? There should be 34,995.4. So we're going to take off that 0.4 and say there should be approximately 34,995 or maybe even 96 that will work. Okay, because you can't have 0.4 of a light bulb. Now, could you use a proportion with that? Absolutely. You could have said, well, 692 is to 700 as x is to 35400. And then you could have cross multiplied and divide. So you could do 692 times 35400 and then divide by 700, and you would have got the same answer. Either way, I really don't care which way you do it. Now up here in this probability, if they would have actually have asked you for the probability, I'm going to make a little box and just say, if asked for probability, you would need to reduce here. But they didn't ask us for the probability, they asked us to use our probability to apply it to something else. But if they did ask you for the probability itself, you would have to reduce at that particular step. You know, figure out what goes into 692 and 700. That's it for the lesson. If you have any questions, there is a lesson check in the book that you can complete and come back with lots of questions.